Okay, it's confession time. It's confession time. I'm sorry. Gotta come clean. So earlier I said that all the metal you see, all of the iron you see, it's going to be ferrite with some cementite mixed into it. That you're not going to see austenite still there. And that's not 100% true. There is a way to have austenite survive to room temperature. And well, how does it do that? Well, it does it by being really ridiculously subcooled. So when you really ridiculously subcool liquid metal, or just austenite, it is going to form something completely different. So this is what's called Martensite. So Martensite is a body-centered tetragonal crystal structure for the iron and the carbon atoms. Okay, it's always going to form this. So you can have a carbon atom at the top, the bottom, and in between all of these guys. It won't have it anywhere else. Now, if you look over here, you might also realize it's called Martensite needles. So the black is the Martensite, the white-ish is the austenite. And so Martensite is going to form needles when you subcool this quickly. And if you can think about that, needles, well, needles do not like to bend, they like to snap. And so, yes, this is a very, very hard, but very, very brittle metal. You think of more like metal glass. Okay, so how do we get it? Well, you just subcool it ridiculously. And if you subcool it like crazy, what you will get is Martensite. Okay? What you will get is Martensite. And the degree to which you subcool it will tell you, well, how much of this Martensite do you have? Now, this is a rapid transition. And since, as you can see here, it does not depend on temperature, this is a diffusionless transition. It's just forming it right where it is. And it's only going to depend on what temperature I cool it to. So, if I go with slow cooling from austenite, it'll form ferrite and cementite, in different structures of that, maybe bainite, maybe perlite, maybe one of those. If I instead quench it, so like you see it in old blacksmith movies, they smack on the sword and then they stick it in the water. Well, they're quenching it and they're trying to form this Martensite because that makes it very, very hard. So Martensite by itself is a single phase. It's a bicentennial tetragonal structure. And because it's bicentennial tetragonal, it has very few slip planes, which means that it is very, very brittle. It does not like to bend and stretch. So it's not going to be the best thing if you want something that is flexible or can, like a hammer it would be horrible to have a hammer made of Martensite because that hammer is going to shatter when you smack something. However, if I had a softer, a ferrite hammer, it'd be able to bend a little bit when I smack something and actually be able to hammer the nail. So you need this only in times when you need a massive amount of strength with that, and you're okay with it being very, very brittle. Otherwise, this is not for you. Okay, so with this, we've gone through all of our structures except for tempered Martensite. That's at the end. We'll come to that one later. Just think spheroidite, but for Martensite. And so you can see that how you cool something down and the speed at which you cool it and the temperature at which you cool it is going to change what structures exist in your final metal. And then it tells you how the properties are going to change. So, with that being said, let the learning continue. See y'all later. Bye-bye.